Yeah, thank you, Vincent, for the presentation and of course for organizing and also for all your efforts when my talk had to be moved. We are finally here and yes, talking about organic cells for the first time in this series. And also as my title says, I'm talking about state-of-the-art organic cells. What do I mean about this? Well, nowadays, usually when we use this term, we are talking about blends in which the acceptor is a non-fullerene. I have put the example here, the most famous, which is Y6. And I mean, most of my talk will be based on this molecule. And I actually also added a picture here of one of our solar cells when Y6 is blended with PM6. We have only 100 nanometer layer here, but we can get short circuit currents above 26 milliamps per square centimeter. We can get different color, different thicknesses, different transparency. And this is actually one of the key selling points for organic solar cells. But of course, efficiency needs to be improved. This is always what we are after. And here at the University of Potsdam, we look more at the fundamentals. We try to know what is happening in the different states that play a role in the operation of organic solar cells and how we can actually come up with some guidelines to increase the efficiency further. Well, I've already mentioned efficiency a couple of times, so let's put into context, where are we now? And to try to show you a plot of why non-fullerene acceptors have actually taken over in organic solar cells. So fullerenes, they had a long life, they increased in efficiency, it was nice, we learned a lot, but it was from 2013 or so that the efficiency reached sort of a steady value, not much was going on. And then people started using non-fullerene acceptors again, coming up with new designs, and actually efficiencies were just boosted. And since 2017, now 2021, efficiencies have gone from 13% to we are very close to 19%. I think it has even been reported, but not certified yet. So yeah, very close to our PCE goal of 20% and getting there. So it's getting exciting. It's been getting exciting for some years now. And here at University of Potsdam, we wanted to learn more about what's the difference between NFAs and fullerenes, and well, whether these differences are beneficial or not, how can we actually push things even further? To show you some of our results, I would like to just briefly talk about organic solar cells. I'm sure you've heard this many, many times, but just for the flow of the talk, let me just say it once more. So we know when we are looking at organic solar cells, we are looking at a blend of two materials, a donor and an acceptor. And we create what we call the bulk heterojunction. The reason why we need this is because in organic semiconductors, upon light absorption, we will create a strongly bound exciton because of the low dielectric constant. Now, this exciton within its lifetime needs to reach a donor-acceptor interface where it can separate into free charges. Energetically, let me show you here an example from back in the day when PCVM was the rule. Then most of the absorption was actually happening in the polymer. Then we would have electron transfer and we would create the so-called charge transfer state. Now this was still bound, but it could eventually separate into free charges in what we call the charge separated state. These terms will keep coming up, so this is why I wanted to show you this. Now, when we talk about NFAs, the energetics change a bit because now we have molecules that have a lower band gap and they have a strong absorption coefficient. So what we get is complementary light absorption. Now, high energy photons are absorbed by the polymer, low energy photons can be absorbed here. And this is what gives us the high JSCs that I was talking about. Another key feature of NFAs is that actually the lowest excited state is a singlet exciton, and it has also high photoluminescence yield, so it emits also strongly. And this has been pointed out as a source for low open circuit voltage losses. There are many other things that set NFAs apart from fullerenes. But to look more in depth into them, we actually focus, and most of my results that I will show here will be on the blend of PM6Y6, which I already mentioned when I show you the solar cell. So this is our polymer, and this is Y6. The key features that we wanted to look at, and we did them chronologically, so I will start by what we looked at first. At the very beginning, when people were investigating more NFA blends, what they realized is, well, we have a low energy offset between the HOMO, lower than it used to be for electron transfer, but now, since the Y6 or the NFA is absorbing light, we also need a driving force. And we need some sort of offset to have Hall transfer. So in terms of this, we looked at free charge generation, and this will be what I will be talking about first. Then something else that I already mentioned is that Y6 has high photoluminescence, and we wanted to learn more about what is the role of this in the emission properties of the actual blend and all the states that are involved in recombination and also in generation. And this is what I will be showing in the second part. And then lastly, when people have been reporting PM6Y6 layers, they always talk about the high crystallinity and how Y6 tends to aggregate and form clusters. And well, this goes hand in hand with low energetic disorder values. So lastly, I would like to talk about the role of these values, whether they actually still play a role in these high efficiency blends or not. So, and actually whether they do, in which photovoltaic parameter do they play the biggest role, and this will be the last part. So let me jump right into free charge generation in PM6Y6. And what we looked firstly, it's at the field and temperature dependence of charge generation. We did this by using a technique here, which is called time delayed collection field. I will briefly introduce it because it helps me to show you why we can actually look at the field dependence. And this is because when we have our device, we can hold it at different given pre-biases. So we can go from high reverse bias to close to VOC. At high reverse bias, it could be that the field is actually assisting charge generation. After a short laser pulse and a short delay, we will apply a very large reverse bias to collect all the photogenerated charges. Now, since we are using a laser pulse, we can use different excitation energies, and we can excite the PM6 and the Y6, or just the Y6. And even what we did, we went lower in energy to excite the tail states of the Y6. And what we observed is that by using a wide range of excitation energies, charge generation was field independent, and it was very efficient in all cases. And actually having more energy did not further assist on generation. We look farther also into the temperature dependent, here shown for 2 excitation energies. And what we observed is that even as we cool down their samples, we still had field independent generation, and we extracted not many less charges. Well, then, of course, what we see is that we have charge generation that is field independent for all the excitation energies and the temperatures tested. And actually, since we extracted very efficiently, still at low energies, we saw that we have a very small activation energy for free charge generation. Now this is clear, but there can be different mechanisms to explain why this is. And one of them is closely related to the chemical structure of Y6. So we have this structure in which we have acceptor, donor, acceptor, donor, acceptor. This plays a key role, and also it gives a large quadruple moment to the molecule. Now, it has been shown for many polymer NFA systems that this quadruple moment, what it essentially does at the donor-acceptor interface is that it creates an electrostatic field, and it can bend the bands exactly at the donor-acceptor interface, right? This will lower the dissociation barrier for the charges. it will lower the difference between the charge separated state and the charge transfer state, and it will efficiently separate charges. However, as it has been shown in these papers, this gives a limit to how much we can play around with these quadruple moments, because actually we need to have an offset to begin with. Otherwise, if there is no offset between the HOMO-HOMO or the LUMO-LUMO, we will actually block the charges. We will create a barrier, which is the opposite of what we observe in PM6Y6. So PM6Y6, good for this. Other blends, the offset still needs to be there, and it is considerable. Otherwise, this would not work, this mechanism, this model. But this is, of course, much better explained here. They did a very good job. I recommend reading it. Yeah, so, but another mechanism actually points to the molecular packing of Y6 as playing a big role in charge generation. So what Zhang and his colleagues showed is that we have just one Y6 molecule in contact with a PM6 segment. Upon excitation, the distance between the electron and the hole will be 22 Armstrong. Now, if what we have is a cluster of Y6 molecules, the distance will be almost doubled. So this will actually delocalize our charge transfer state and lower the dissociation barrier as well. So it will help to generate charges. So we showed that generation is very efficient, and it's related to the Y6 structure and how it likes to pack. So these are already some important guidelines that we see from literature and also our results. And this is what I wanted to show for free charge generation. So that now I will move into the emission properties and recombination in PM6Y6. To look at this, I talk about the photoluminescence of Y6, right? So, but what we wanted to do is first of all, measure the PL of the blend in a full device. So we have our transport layers and we have our electrodes. So whatever interference effects we may have are there. And what we did is measure the signal at open circuit and at short circuit conditions. Now, when we are at short circuit, we would expect that all free charges are efficiently extracted, right? And at open circuit, what we are doing is we are forcing the charges to recombine. Since the signal is very similar, what we concluded is that what we are seeing is actually the radiative decay of Y6 excitons, which do not care about the field. This has important implications, but some of them we can look at when we compare actually the PL and the absorption. So what we did is we measure sensitive EQ-EPV, and we use reciprocity from the PL, and we saw that it can explain very well the EQ-EPV. So the first drop and also the second shoulder that we observe here. Since we know that the PL is mostly Y6 excitons, this would mean that the absorption in the blend is also mostly Y6 excitons in this tail. This we could corroborate further because we measure EQ-EPV as a function of temperature. And what we see is that this second bump is reduced when we cool down. So this is actually the absorption of thermally excited vibronic states of the ground state to the vibronic ground state of the excited state. So essentially what we have is the 0, 0 and the 1, 0 of the singlet. So contrary to what we had thought before, we cannot discern the CT absorption in the EQ-EPV spectrum, even down sensitive as 10 to the -7, and also not in the PL. This is just the vibronic progression. This is already one conclusion, but we wanted to look further, and we wanted to look at the PL versus the electroluminescence. So now what we are doing is we are injecting free charges into our device, and the signal clearly goes down, but something interesting comes up actually when we look at the normalized spectrum. The EL has a very similar shape to the PL, and it peaks the 0, 0 at the same energy, which means that actually in the EL, we also have mostly Y6 singlet excitons in what we are measuring. But if we, in the normalized spectra, subtract the PL from the EL, we see that that we have a low energy contribution in the EL that shows up, which could be most likely the CT. But importantly, this is less than 10% of the total yield that we are recording. And I will come back to this point. But what's interesting now is that we've shown that if we inject charges into our sample, some of them will be reformed into the singlet excitons, and this is mostly what we will be seeing. So something that we wonder about is, can we actually quantify the offset between the singlets and the free charges? And this is actually possible if we consider the thermal activation for this repopulation from free charges to Y6 excitons. So what we did measure to look at this was the EL as a function of temperature. And what we can see is that indeed, the main excitonic peak goes down with temperature. This is not the case if we just measure, for example, PL of a polystyrene blend with Y6. The EL intensity goes down because we are hindering this repopulation of Y6 excitons. And this can actually be fitted with an activation energy, which is this offset between the singlet and the charge separated state, which we estimated to be at around 120 milli-eV. All right, so from all these conclusions that we drew in this study, we wanted to summarize everything in an energy scheme. So to say, to tell people what's happening, what we think is happening. And we know that we have the Y6 exciton, we have the charge transfer state that right now we don't know where it falls. It's still not discernible as I show you, and we have our charge separated state. Since most of the PL and the absorption, so the EQ-EPV that we saw was Y6 excitons, we were able to calculate the chemical potential of singlet excitons in the blend in a full device. And actually this value was very similar to the quasi-Fermi level splitting of free charges, which is the VOC of our device. What this tells us is that we indeed have equilibrium between exciton and free charges. Now, when we injected free charges, we saw that we had a contribution, a low energy contribution, which was only 10% of the total ELQY that we were measuring. This was mostly coming from the Y6 exciton. Now, we have a film of Y6 and we measure its PLQY, right? So this is the value, and this is the probability of one exciton in Y6 to recombine radiatively. Very nicely, we can relate this value to the ELQY. And what this tells us is that from the injected charges, only 0.6% are reformed into Y6 excitons, which means that 99.4% of the recombination happens through this very weakly emitting, which we could even call dark from the ELQY value that it has, low energy state. This low yield of reformation can be explained by the barrier that we measured. So actually this exciton reformation in this blend, so in PM6Y6, has little effect on the VOC. And it's actually the recombination at the interfacial CT that must be reduced. So either we increase the radiative contribution of the CT state, or we come up with a way of reforming more free charges into exciton so that the exciton becomes more radiative, and then it would play a bigger role, as has been shown in other studies. But for PM6Y6, this is the scheme that we came up with. With this said, I can move into the last part, where I will talk about the role of energetic disorder. This has actually been part of the last work I've been doing for my PhD. It has just been submitted. And when I talk now about energetic disorder, I talk about the energetic disorder for free charges, so for the charge separated state. And we kind of stumped into this topic because what we started doing is comparing Y6 to one of its closest derivatives, which is N4. N4 has more elongated side chains here in comparison to Y6. And when it was firstly reported, what they showed is that due to this elongation, the morphology changes. So we have more preferential edge on versus we know that PM6 Y6, by the way, this comparison was always done when blending the NFAs with PM6. We know that PM6 Y6 has always preferential phase on, and also it has a lower domain purity they showed. So this was interesting for us because we knew that the morphology of Y6 and of the blend plays a role, right? So we wanted to test N4, see whether we could see differences and where this difference come from and whether they are related to morphology, of course. We did measure morphology ourselves. Here you have some two-dimensional plots of GWAX. This is just the scattering of the substrate, so just ignore it. What's interesting is that we have a stronger phase on pi-pi stacking in the PM6Y6 than in the PM6N4. Also, the lamellar stacking is more isotropic in PM6N4, and it's hard for me to show it here, but we've looked at it and we have more of an amorphous contribution here in the background in the PM6N4. So we have clear difference in the morphology. Now the question is, how is this actually affecting the photovoltaic parameters? So I want to show you some JVs here, the comparison, and interestingly, the JSC does not change much, neither does the fill factor, but we see a clear difference in the open circuit voltage. It actually drops for PM6M4. Since this was the parameter that it looked like we had to focus on, put our efforts on, of course, what anyone would say to first look at is the energetics, right? So it could be that we simply have different energy levels, but we looked at the EQ-EPV, and what we observed is that actually it is blue shifted for PM6 and 4, which gives us an effective band gap that is higher in this blend. So essentially, we have higher voltage losses coming somewhere that at the end gives us a lower VOC. So what we did, of course, was look at recombination. We use 3 different techniques. All of them pointed to bimolecular recombination in PM6M4 as well as in PM6Y6. So we could calculate the bimolecular recombination coefficient. And to our surprise, recombination is slowed down in PM6N4, but we do have a higher VOC. So it's not really explained by this. So after some discussions, we were like, okay, can we blame disorder? So we know that we are talking about organic semiconductors. We have a density of states. Disorder will broaden this, and this means that we will have tail states that will go deeper into our photovoltaic gap. If we photogenerate charges, the Fermi level splitting of these holes and electrons will be lower because they will be sitting deeper, right? So disorder will increase our voltage losses and will decrease our VOC. So we wanted to know whether this is what's happening in PM6M4 in comparison to PM6Y6. Firstly, then, what we measure was, of course, the disorder of the LUMO and the disorder of the HOMO. We don't see a very big difference in the LUMO, but we see a clear increase for the HOMO of PM6 and 4, which explains why the whole mobility is 1 order of magnitude lower. But we didn't, we had proof now, right, that the disorder is higher in the HOMO, essentially, of the N4, but we didn't want to stop here. We wanted to look another way to check the effect of disorder. And what we wanted to look at is a non-geminate recombination. But I already told you that the recombination order was 2 for both blends, not very different, but we looked at different temperatures to see what could come up. And what we saw, we look at the recombination rate as a function of the carrier density, and the slope is for all temperatures and for both blends fairly close to 2. So there is not a very huge difference between the 2 blends. But still, we already did these measurements. We had more information from it, which is actually, we had the carrier density as a function of the open circuit voltage, which can tell us about the M factor, and also the generation current as a function of the open circuit voltage, which can tell us about the ideality factor. Now at 300 Kelvin, still we don't see much difference between the two blends. Values are close to 1. Things get interesting now as we cool down our sample. And I want to show you the difference for the M factor because it's clearer. We see for PM6Y6 that as we cool down the sample, so we lower the temperature, we need to increase the slope in order to fit the data, right? This means that the M factor is not changing much between these temperatures. But if we compare it to the PM6 and 4, we see that all data falls together. The slope doesn't change much. And this could only be explained as we cool down if the M factor is actually temperature dependent. And the case is the same for the ideality factor. This has, again, some implications, and maybe what I'm trying to say is not so clear in these plots. So what I did here is to actually plot the factors that I was telling you about as a function of temperature. We have the recombination order, which is close to 2 and temperature independent. And the clear difference is for PM6 and 4 that the M factor and the ideality factor increase as we cool down. These tell us about the dominant recombination pathway in each of these blends. So you know the most famous one is if we have two Gaussians, right? And we have free recombination with free or free with trap, this wouldn't matter. We would always measure an M that is close to 1, a recombination order that is 2, and an ideality factor that is equal to M and 1. This seems to be the case for PM6Y6, temperature independent factors. Now, from the models proposed by Dita and Andreas, there's only one model that could explain what's going on with PM6 and 4. That it's that the recombination order does not change with temperature, but the M factor and the ideality factor do. And this model is actually when we have a Gaussian, and free charges in this Gaussian recombine with trapped charges in a broader density of state that has an exponential-like tail. Now, in this case, the M factor and the ideality factor would depend on temperature, and their definition would be by this equation, in which T0 is the characteristic distribution temperature of the exponential tail. Important to tell you, by the way, that here I have drawn the exponential tail in the HOMO because we measure a higher disorder in the HOMO of PM6 and 4. Also, so now we took this equation and we actually fitted our data and we could get a T0 value. And actually it fitted quite well, the fact that, that the factors are increasing. All right, so also here you have all these equations that I have put here for each one of these density of states. And this is important because if we have a model, if we know how the recombination is happening, we can actually estimate the quasi-Fermi level splitting. See, if we can estimate the quasi-Fermi level splitting, we can predict our VOC. The equations will of course depend if, for example, I have electrons in a Gaussian, because then I have to consider the disorder of the Gaussian. But if I have trap holes in an exponential tail, what I have to consider is T0, as I just showed you, right? We have these values because we determined them experimentally. Something is missing from that prevents us from using these equations, and this is the free carrier density in our devices. But Fong in my group did something very nice. He actually measured photoinduced absorption as a function of temperature, and he could measure the carrier density down to 100 Kelvin. And what we see here is that the carrier density increases in our device as we cool down, and that we can actually use these values now to reproduce our experimental data of the VOC as a function of temperature. So we have PM6M4 here, PM6Y6 here. Now, if I use the Gaussian model, I can explain nicely the PM6Y6 data. If I use it for PM6 and 4 in the high temperature regime, it works quite well. By the way, something that I forgot to mention here in these fittings, I always kept the band gap as a fitting parameter, right? That I obtained, and it was not much different between the two. All the rest were experimental values. So yeah, what is important to say is that we actually need the experimental Gaussian, the exponential Gaussian model to explain the low temperature regime in the PM6 and 4. Because what this model tells us is that for the Fermi level splitting of holes, we don't have a temperature dependence. So that's why this data is much flattened out, and why, if we would use the Gaussian model, it would be shooting up. It would not be representing what we are actually measuring. So important conclusions here would be that energetic disorder has a pronounced effect on the absolute value of the VOC and its temperature dependence. And it also plays a role in PM6Y6. I could not have fitted this data if I would not have considered the disorder of the LUMO and the HOMO. So yeah, disorder needs to be taken into account when we look at the VOC and the voltage losses, even in the high performing blends such as PM6Y6. But PM6Y6 benefits from narrower band gaps. It's not the same as PM6M4 where we have this broadening and then the VOC suffers, even we start from a higher, from a blue shifted EQ-EPV essentially. Also something to take home from this data is that when we measure the carrier density and we decrease the temperature, it actually increased the N. This indicates that we have actually a downhill driving force for free charge formation. So free charge formation is not temperature assisted. Otherwise, as we would cool down, we would not be having more free charges. And so yeah, we probably have a combination of this band bending that I was telling you about, but energetic disorder seems to be also playing a role. And from this model that we have applied here, which considers an equilibrated population of states, our free charges are always well below the Y6 singlet exciton. And this is the driving force essentially. All right, so with this, I would like to move into the conclusions. I've had different ones through the different points that I've talked about, but I just put the main things here. So for free charge formation, we've seen that we have a low barrier and that actually morphology and the microelectrostatics are very important. This would be the guidelines when we are looking at chemical design. When we are looking at the emission properties and recombination, we see that the radiative recombination, when we can record, is dominated by Y6 excitons. However, most of the recombination proceeds through a low energy weakly emissive state. So as I said, for guidelines, either we increase the radiative recombination here, or we somehow increase the radiative recombination of excitons and also the repopulation of those. And finally, for the role of energetic disorder, I have shown that PM6Y6, essentially, yes, it has low energetic disorder. So it benefits from narrower density of states, but still it's influencing its VOC value at room temperature. We need to consider it when we look at voltage losses, and also when we look at the progression of the VOC as a function of temperatures. For example, when we try to get the CT energy from fitting the VOC versus temperature, we need to think that we actually have a disorder that still plays a role. Yep, this is what I wanted to say. Also, of course, give some thanks, mostly to the people at Potsdam, of course, but also all my collaborators, because without their input, none of what I showed you would have been there, actually. And yeah. Finally, back to the conclusions, and thank you for joining. I forgot to say that at the beginning, but I'll be very happy to receive many questions.